Alright, so now we get to the version of the fundamental theorem of calculus for line integrals, which is imaginatively called the fundamental theorem of line integrals, here denoted by the memorable acronym FTOLI. So it goes like this. Suppose we have a conservative vector field. That means that our vector field is actually the gradient of some potential function, little f. Then the line integral of f dc over any curve c is just given by the values of the potential function at the endpoints. So that simplifies the evaluation of an integral greatly. Now, if I were being precise, I should point out that f is supposed to be differentiable and the curve needs to be differentiable as well. But that's fine. So let's see. So what is the proof of this? Why should it be true? Well, let's take a look. So we'll dig under the hood a little bit here in the integral f dc. Now we just said that capital F is supposed to be conservative. So that means that I can write it as the gradient of the potential dotted with dc. And so if I choose some parameterization, then I need to write this in a little bit more detail. So on the parameter interval from a to b, we have gradient of f at the location on the curve dotted with c prime of t dt, like so. Okay, and then if I write out the components for this, let's see. So my gradient function here, this is going to be the partial with respect to x, partial with respect to y, partial with respect to z for this part right here. And over here I'm going to have dx, dy, dz, all as functions of t, because we're doing it with parameters. So when I do that dot product, I'm going to have integral from a to b, and then I'll have partial of f with respect to x from the first part of the gradient times dx dt from the first part of dc, and then I'll have df dy dy dt, and I'll have df dz dz dt, and these will all be added up. So there's our dot product, and this whole thing of course is integrated with respect to dt. And then you look at this and go, oh, I have seen you before. I know your name. You are the derivative of f of c of t by chain rule. So doing the chain rule in reverse, we see that this is the integral of ddt of f constrained to a curve, integrated with respect to t. And then you look at this and you say, hey, and I have seen you before. You are one half of the fundamental theorem of calculus, the regular single variable version from Calc 2. So that means that you are going to just be given by integrating the thing that's being differentiated, evaluating the thing that's being differentiated across the endpoints. So that's by the fundamental theorem of calculus in one dimension from your previous calculus course. And then we just evaluate this function across the endpoints. So we have f of c at b at the end of the curve, and f c of a at the beginning of the curve. There we go. So that solves our theorem. Here's a little end of proof symbol. Dun, dun. A box. You get a box. All right. So that's why this theorem is true. And there's a couple of interesting corollaries. So a corollary is a theorem that you get basically without having to do any work from a theorem that you already proved. So it's like a cheap ripoff. So if f is conservative, then we can see that the integral of f dc depends only on endpoints and not on the path taken, right? And so it's independent of path is how this property is, sometimes expressed. So, in other words, if f is a gradient, then the integral of f dot dc is just f of the endpoint minus f of the start point. And so you might say, okay, but how often does this come up? And the answer is all the stinking time, especially with physical applications. So things like gravity, that's a conservative vector field. Things having to do with electricity and magnetism, they all have potentials. So those are conservative vector fields. So the upshot is that means that if you have, say, some tower and you've got, some staircase that goes around all the way to the top, and you have to pick some big heavy weight and take it all the way up to the top of the building, or if you're clever and you just build like a little hoist here and you haul it up on a rope and it just goes straight up and onto the top, you've done the same amount of work either way. Even though one of them looks like maybe it's a lot more because it involves, like all of this dragging and walking and laborious, like heaving. In terms of exercise, the amount of exercise might be different, but in terms of the physical quantity of work, well, we just took this object from point A to point B. It doesn't matter if you do it that way or by bringing it up some other route. You'll do the same amount of work. And another corollary is that if f is conservative, and C is any closed path. So remember, that means that you end where you start. So it's a closed loop. Then the closed integral of f dot dc is, 0. Because you have the same quantity, you have little f of start equals little f of end. So these guys just cancel. All right, so that means that actually if you were to drag that box like all the way up and then drop it off the edge and then drag it all the way back, you've done 0 work.